And thanks for the introduction. And thank you all to attend my PhD defense. And also thank the people online. In the next 45 minutes, I'm going to present the work derived from my PhD project, that is advanced modeling of biomass, pyrolysis, and combustion. Let's start. My project consists of two parts: kinetic modeling of biomass pyrolysis and CFD simulation of biomass combustion. So I'm going to present the two parts separately. Besides this, we also briefly introduce the introduction, main contributions, and future perspectives. From the reports of International Energy Agency, the biofuels or biomass is still the largest renewable source supply, and biofuels are very potential in the near future. So my project aims at contributing the conversion from biomass to biofuels or bioenergy. From the technology point of view, biomass conversion can be roughly divided into three categories: physicochemical conversion, biochemical conversion, and thermochemical conversion. Among them, thermochemical conversion, such as pyrolysis and combustion, are more efficient, usually, in terms of producing biofuels and recycling energy. Moreover, pyrolysis is also a sub-process of combustion. So therefore, I intended to investigate biomass conversion via pyrolysis and combustion technologies. For biomass combustion, kinetic modeling is the fundamental of understanding and predicting the conversion process. The conventional models are based on the Arrhenius type equation. That is, the conversion rate, d alpha divided by dt, can be calculated by the kinetic constant Kt times the reaction mechanism F in which Kt is a function of temperature governed by the kinetics A and Ea. So almost all the work in this mode are derived from the two sides. One is the evaluation of kinetics, and another one is the determination of the reaction mechanism. For instance, the model fitting and the model free method for the former, and the master plot for the latter. While the work from the two sides also has some connections and influencing each other. In addition, the determination of the reaction mechanism, I think, is not adequate. It needs to be emphasized. Apart from the conventional model, and there is a new way to describe the pyrolysis process that is based on some distribution functions, for instance, Weibo distribution. And from the figures, we can see the plots of the Weibo distribution, the density function and the cumulative function are very similar to the Arrhenius equation for a certain range of lambda and k. For instance, lambda equals 1 and k is 5 here. That shows the potential of using these distributions to predict the conversion process. Here, I would like to talk a little bit more of the conceptual ideas behind the two models. For the Arrhenius type model, it's based on the collision theory, actually, and it's an analytical physics method. The reaction occurs due to the effective collision of the molecules. And how to define the effective collision is by the activation energy. The reaction occurs, the colliding molecules must overcome the energy threshold, and that is represented in this equation Ea here. And the pre-exponential factor A actually represents the collision frequency. And on the other hand, for the distribution-based models, it's model the pyrolysis process in a statistical way. And it treats the overall pyrolysis process as a mass failure process. And the conversion is governed by the CDF, which is ranged from 0 to 1. And the conversion rate is governed by the PVI. So if we look a little bit in depth, we can see actually there are some similarities between the two series. That is, the molecular collision is random, and the happening of the effective collision actually is a statistical event. So here comes to the first research question: how to generally model the pyrolysis process in a statistical way, and what the relationship with the conventional model. Okay, let's move to the combustion part. For biomass combustion, CFD simulation is used in my study, and municipal solid waste, or MSW, grid boiler is selected as an investigation target. For a typical grid boiler, the feedstock is fed onto the grid and accumulates to a porous fuel bed, where the solids are heated up by the flux from the freeboard and converted to gas and ash. Consequently, the released gas from the fuel bed flows into the freeboard, and where the combustibles are burned out by the secondary air supply and flows out after several exchangers or water paths. So in this scenario, the coupled strategy is always being used for modeling such a grid boiler. Namely, model the freeboard and fuel bed separately and then couple them together here. Normally, the freeboard simulation is a little bit easier and can be carried out by some well-developed CFD solvers, such as ANSYS Fluent or OpenFOAM. But for the fuel bed, it's a little bit complicated. Self-development models are usually needed. So let's look a little bit deeper for the bed modeling. According to the different modeling approaches, the bed model can be divided into three thoughts: the empirical model, the Euler model, and Euler-Lagrange model. For the empirical model, the overall fuel bed is manually divided into several stages and only consider the overall mass and heat balance. So it's a very simple model. It's just to facilitate the CFD simulation in the freeboard and contributes very little to the fuel bed investigation. While for the other two models, they are comprehensive model. It means then solve the governing equations and predict the overall conversion process with considering the reactions and so on. The major differences between the two models is a way of treating the solid phase. For Euler model, it treats the solid phase as a continuous phase, while for the Euler-Lagrange model, it treats the solid phase as discrete phase. So under Lagrange framework, it allows to check each particle movement. However, it takes lots of computational resource, making it difficult to be implemented in big or large industry scale boiler. So finally, I decided to develop a comprehensive bed model under the Euler framework, and then couple it with the freeboard simulation to accomplish the entire boiler simulation. The objectives of my project is first to develop a universal description for the kinetic study of biomass pyrolysis, and of course considering some applications and kinetic studies of the woody biomass. And also, second is for the biomass combustion. I intended to simulate the entire MSW boiler, that's including the fuel bed development and the freeboard simulation, and also couple them together. So my thesis is structured as two sections: the report and the selected papers. For the report, chapter 1 is the introduction, and chapter 2 is part 1, kinetic modeling of biomass pyrolysis, and chapter 3 is part 2, advanced simulation of MSW combustion, and chapter 4 is the summary. For the papers, paper A and B are derived from part 1, so it's included in chapter 2. And the paper C and D are derived from part 2, so it's included in chapter 3. For the paper D, it was under review when I submitted my thesis, and now it's published. Okay, let's go to part 1. The motivation of doing such a kinetic study in my project is the complexity of the current kinetics. That makes people suffering when you use them. So the idea is, should we find a general or universal modeling approach to describe the pyrolysis process? And the answer is yes, and which has been tried in that paper. And it's a very good attempt, I think, and showing the potential, showing the possibility to do such a universally model work. But it also has some limitations. For instance, it's only for the first order reactions. So inspired by this paper, I decided to go further in universally modeling biomass pyrolysis. Okay, first let's go to the model derivation. And I know the equations are very boring. You will not listen to me anyway. So I just skip this and without further explanations. If you are interested, we can discuss later. And here I would like to show the final results of the universal description. For the blue equation, that indicates all the first order reactions is governed by a statistical distribution, where the conversion rate is governed by the cumulative distribution function of the distribution, and the theta-based conversion rate is governed by the probability density function. For these two functions, is only the function of the variable theta without any other parameters or variables, and moreover, it only depends on the reaction models we selected. For instance, the first order or second order. So that's why I call it a universal description. And here I summarized all the expressions for the universal description, and yeah, and also with some characteristics. Here we can clearly see the reaction, all the order reactions and the nucleation reactions belongs to one category. Okay, here is the plot for the first order reactions. And we can see it's precisely consistent with the standardized JEV distribution. I think that figure explains why the JEV distribution can be used to analyze biomass pyrolysis process, and that has been conducted in lots of studies. And also for the plots for other common reaction mechanisms, and they have the same, yes, peak potential, I think, the theta value. And the unique characteristics can be used to analyze the biomass pyrolysis process, which will be discussed later. Okay, it's time to call back to the inspiration paper. I mentioned before, I did such a kinetic modeling work is inspired by a paper. And for that paper, here is the model actually in the paper. And it looks different to the universal description I derived. And I reproduced this model, and the finding is the larger lambda is, the better fitness, the better to the Arrhenius model is. The reason behind is if lambda is big enough, and this equation actually equals to the universal description I derived for the first order. As shown in this figure, if lambda from 20 to 200, and the two models actually are getting closer and closer. Okay, before I demonstrating the model applications, I would like to briefly introduce the experiment setups. Cellulose and popular wood are analyzed by a thermal analyzer to obtain the TGA data. And cellulose, as one of the major components of biomass, the data will be the pseudo components. The data will be used for the model validation. And the popular word as one of the real biomass, the TGA data will be used to demonstrate the model's applicability. So let's move on. Application 1 is to identify the conversion rate. From this table, we can see at the conversion peak, the theta value is fixed, and this theta is a self-defined variable. And if we plot theta versus temperature, then if we know the reaction mechanism, we can easily identify the peak protection. So that's a simple one. And application 2 is a simplified kinetic model, or is called to predict the conversion rate. As we derived in previous slides, and the theta-based conversion rate is derived. And if we substitute F alpha and G alpha into this equation, then we can obtain we can clarify the relationship between the theta-based conversion rate and temperature-based conversion rate. That's important. In the introduction part, I said the first research question, it is how to universally describe the parasitic process by a statistical way, and also what's the relationship between it with the conventional model. And this equation, I think, clearly answers that question. So that's the equation between the universal description with the conventional kinetic model. But this equation is not simplified anymore because PU here is a temperature integral which has no analytical solution. So I introduced an approximate equation PU here, and this equation is also used in KX method. And then we can get a much simpler equation as described here. And then if we separate the d alpha dt to the left side, then we can get another expression of the of how to calculate the conversion rate other than the typical Arrhenius equation. If we compare with the typical Arrhenius equation, we can see for the new equation, it only contains one kinetic parameter EA, because d alpha d theta is a certainty if the reaction mechanism is certain, and it's independent from A and heating rate. Okay, let's see the comparison results. For this figure, I compared the calculation results from the two equations using the same kinetics. And we can see for the first order, second order, and the third order reactions presented here. And for other reaction mechanisms are presented here. From these results, we can conclude that for the order reaction mechanism and R2, R3, and D3, I would say the difference is minor. But for the nucleation reactions, the difference are remarkable. The reason why it's like this, and I suppose it's probably due to the approximate equation PU used. Maybe it's not that suitable to the nucleation reactions. Moreover, I did an experimental validation using the cellulose TGA data. For these three figures, we can see both the conventional Arrhenius model and the simplified kinetic model show good agreements with the experimental data. While for this figure, using the low quality kinetics, the simplified model performs better than the conventional one. The reason, I think, maybe because of there is only one kinetic parameter in the simplified model. So if we use a low quality kinetics, it will introduce less calculation error. Okay, besides these two, there are other two more applications. Third one is determination of the reaction mechanism and the fourth one is evaluation of kinetics. But for these two equations, actually based on the same equation with the simplified model of the application 2. So I will not go further here, and just briefly show some results. If you would like to know more details, you can refer to my thesis. Okay, let's summarize part 1. For part 1, a universal description for solid fuel pyrolysis is derived for all the commonly used reaction mechanisms, and then the unique characteristics are a review of the universal descriptions, and then 4 applications have been conducted based on the universal description, including the simplified kinetic model. Okay, let's move to part 2, CFD simulation of biomass combustion. As mentioned before, the coupled strategy is used for the CFD simulation of the boiler. And the freeboard simulation is carried out by ANSYS fluent in my thesis. And the fuel bed is described by a standalone bed model, which is developed by myself. And then I couple them together and manually. The fuel bed model actually was first developed for fixed bed combustor and during my master's study. In my PhD project, it was transformed for moving grade bed model. I wouldn't say my bed model is a breaking new one, but indeed it has some improvements. For instance, the more appropriate boundary conditions and the more comprehensive reactions used in that model. So let me show you the transformation process. The moving grade bed model results was mapped from the fixed bed model results over time. The results along the grid length are mapped from the results over combustion time. So in this way, this model is the 1D transient fixed bed model is transformed to 2D steady moving grade model. So that's the idea. Besides bed model, besides the transformation and the NOx formation is extended in the latest bed model, but it's only for the fuel NOx because the temperature inside the fuel bed model is relatively low. It's not too intensively to occur the thermal NOx reactions. And also the nitrate oxides is assumed the only form of NOx in the bed model because it's indeed the majority one. And the kinetics for the NOx formation refer to the ANSYS fluent theory guide. Okay, apart from the NOx modeling, and there are also some other key updates in my bed model. For instance, the solid mixing due to the grid movement, because it's now in the moving grid bed model, and also the char gasification reactions and the segmented air supply, because the grid is not a fixed airflow, it's a distribution airflow, and so on. Okay, here's a brief summary of the latest bed model, including the boundary condition, including the governing equations for both solid and gas phases, and also for boundary conditions, which at the top surface is the mass and heat transfer with the freeboard. 16 reactions are included in total in my bed model, and including 5 reactions for the fuel NOx formation. I would say it's still global, globally reaction mechanism for the NOx. And the fuel bed model is solved from the discretization. I use the implicit scheme and the central differential scheme to describe the equations. And then the model is coded in MATLAB based on single algorithm. Okay, let's go to the freeboard simulation. It's called the overbed boiler. The boiler is an in operation industrial scale moving grade boiler. Internal rating 750 tons MSW per day, and the grade it consists of 5 individual grades, and each of them has its own air supply system. So that's why I said the primary air supply is not a fixed flow rate; it's a distribution. It's five parts, and also there are 3 temperature measure points in the different position inside the boiler, and the data which we can use for model validation. And the 3D geometry was created in ANSYS specifically, which will be used for mesh and so on. Okay, the mesh. The mesh is created all as a hexahedral structure mesh by ANSYS ICU, and the total cell number is more than 16 million. And the quality in terms of skewness, angle, and ratio is considered good. ANSYS Fluent is selected as the safety solver at last, except for the default setups in Fluent, for instance, the epsilon turbulence model and the reactions. There are 2 UDFs have been compiled in the Fluent simulation. The one is the inlet profile and carrying the bed modeling results, and another one is for the P1 radiation model. Actually, it's modeled the mixture gas radiative properties, and it's called refine WSGGM, which was proven and performs better than the default WSGGM. Okay, the above slide showed all the descriptions of the simulation, and next I'm going to show you the model validation. For the model validation, first for the bed model. Since the bed model is self-developed, so it's essential to check the mass and even element balance. So I just plot the overall mass flow and the major element, that is carbon, hydrogen, and oxygen atom, the mass flow at the bed inlet and at the bed outlet, and we can see the results has no big difference. And there is a mass and time step independence test. Indeed, now the bed model is somehow 2D study, but it's mapped from the 1D trending model. So it's not only to check the mass independence, but also the time step. And the mass independence, as a number from 400 to 600, we can see the results, the key results has big impacts. While for the time step, it affects a lot. And if the time step from 0.02 second to the 0.005 second, and we can see it's quite different. So also considering the computational cost, finally, I decided to use a mass number of 500 and time step 0.01 second in my bed model, and for all the simulations I've tuned. Okay, then it's a coupling convergence. As mentioned before, the bed model is coded in MATLAB, but the freeboard simulation is carried out in ANSYS Fluent. So the coupling procedure actually is did manually. It means first I run the bed model with a guessed radiation temperature and then get the results. And then I integrate the bed model results in the UDF to ANSYS Fluent and then obtain the Fluent results. Meanwhile, export the radiation temperature in the Fluent and then rerun the bed model using the real radiation temperature I exported from Fluent. and then get the new updated the bad model results, and then run Fluently again with the new bad model results. And but in this time, I compare the heat flux transfer rate as the interreaction surface of the freeboard and the fuel bed. And if there's no significant difference between the two transfer rate, heat transfer rate, then I will say the convergence is achieved. If not, then run the coupling procedure again until there's no big difference. And from these results, we can see after 3 times of coupling, I would say the convergence is achieved. All the results simulation, I mean the CFD simulation results in my thesis are after 3 or 4 times of coupling in this procedure. Okay, the experimental validation with the bad model. Actually, the bad model was validated in my previous study by the experiments, but I did lots of updates and extensions now, so I think it's necessary to revalidate it again. I compared with the experiment data and also the previous model and the orange line and the blue line for the current model. For both of the models, I would say it's validated by the experimental data in terms of the solid mass and oxygen and temperature and others. But for some trend, for instance, the char reaction stage, and also for the secondary temperature peak, I would say the current model is more reasonable. Okay, then the inter-simulation validation. In the previous slides, I showed there are 3 temperature measurement points in the different positions of the boiler. And I compared the measurement data with the simulation results, and we can see the error is in an acceptable range. Moreover, I did a hand calculation, or also called equilibrium calculation, as outlets. I just assume everything is burned out or so on. And we can see the results are quite similar to the simulation results. So, so far, I would say the simulation I developed is trustable. And I know for the modeling guy, it's very hard to convince everyone that your model is good. So I did lots of work on this. And for saving time, I will not show you too much results instead, but I will show you the big picture. So after the model validation, I did 2 simulation-based studies. The first one is to investigate the impacts of the feedstock change due to waste classification. Feedstock 1 is the current feedstock or current MSW, and it's incinerating now. Feedstock 2 is a new MSW due to the waste classification. And we can see actually the fuel quality is improved after the classification, and because the moisture content is decreased and the heating value is increased. So I ran 4 cases to compare them. The case 1 is the current operating case, just for validation, and case 2A is to incinerating new MSW while maintaining the operation condition as case 1. And the case 2B is incinerating the new MSW, but I did some adjustments, of course, based on the results of case 2A. So for instance, to increase the secondary air supply, and it means to adjust the acid to PA to acid ratio, and also the PA distributions to increase the mixing in the freeboard and better utilization of the primary air supply. And case 2C is the same compared to case 2B, but just expand 10% of the thermal input, because after the classification, fuel quality is increased. If we maintain the same thermal input as the boiler design, it means the disposal ability will be decreased. So that's why I expect 10%. Okay, briefly show some key results of the case 2A and case 2B. The upper figures are for case 2A and the lower figures are for case 2B. And this is the bad modeling results. First, I would say the combustion trend from the simulation results are very similar, and which we can see the conversion process can be divided into the 4 stages. And stage 1 is corresponded to the moisture evaporation dominant stage, and the case 2, stage 2 is a steady combustion stage, and the stage 3 is a charge reaction stage, and the last stage is the cooling stage. And also for the velocities and the temperatures and the oxygen and the combustibles is all in the expectation range. Well, there are also some differences I would like to highlight. First, at the charge reaction stage, we can see after the air supply adjustment, the charge reaction state is prolonged. And also for the temperature, the highest temperature in case 2B is lower than in case 2A, and that benefits to the great service life. And some colorful figures influence, and the temperature and all the other variables are also in a reasonable range. Well, for the oxygen rich zone, that's I would say the common issue for the grid boiler, especially for the for MSW. And the oxygen rich zone for case 2B is decreased a lot after the, I would say that's due to the distribution of the PA is changed. Okay, beside the colorful figures, I also did a quantitative analysis of the fluid flow. That is the uniformity of the velocity and the turbulence which indicated the mixing of the flow. In general, we expect to increase the mixing and the uniformity together, but sometimes we just cannot get what we want. That's life. And so let me show the results. Because the mixing is increased by the enhancement of the secondary supply. And so it also means in the local area, I mean in the IC noodles, the velocity are increased a lot compared to other areas. So it's not good to the overall uniformity. And the results is also based my expectation. That is, the mixing is increased a lot, while with a small sacrifice of the uniformity. Okay, the second simulation-based study is a co-combustion of MSW and a sludge with industry solid waste, where the industry solid waste acts as a supporting fuel because it's with high heating value, while for the MSW and the sludge, the heating value are very low. And 8 cases are conducted by the simulation with 4 different plants and the different ratios of MSW from 50 to 80%. I still set the MSW as a dominant fuel just to keep the boiler's stability, because this boiler is designed for MSW installation. And also equalize the heating value of the plant to the original MSW. This is to maintain the disposal ability of the boiler. That also means the fuel NOx content is different for the 4 kinds of plants. And also, there are 2 solutions for the primary air supply has been tested. the first solution is a currently used solution, and the second one is after adjustment based on the purpose for DNOx. For instance, the first two subgrades, the distribution of the primary supply is changed a little bit to avoid the oxygen waste in the initial state, because especially under the first subgrade, it's maybe only evaporation. And the third change is to reduce a little bit of the primary air supply, just to reduce the reaction with ammonia to plus oxygen that produce NOx, but enhance the NOx ammonia reaction with natural oxides. And the last one is to increase the little bit of the fourth subgrade, which corresponds to the char reaction stage, and just to enhance the NOx reduction with char. Okay, let me show you the results. Compared to the 8 cases, the NOx emission at the boiler outlet is decreased significantly. This is for the standard NOx emission, but that's also due to the different content, the fuel nitrogen content in the different blends. So to eliminate this effect, I did a normalized NOx emission calculated by this, calculated by the standard NOx emission divided by the fuel nitrogen content in the fuel incinerator. So from this figure, I picked out case 2B as the best case in terms of the NOx emission. Afterwards, I did a calculation for NOx reduction by the air supply adjustment, because there are two kinds of solutions of primary air supply, and for case A to case B, that's the only difference. For example, case 1A to 1B, 2A to 2B. So I did such a calculation to calculate the effectiveness for the NOx reduction by the air supply, which we can see is effective, and the NOx reduction is up to 11.54%. Okay, finally, let's summarize part 2. First, an in-house bed model is updated and transformed to a moving grid bed model, and including the NOx formation. And then the entire large-scale grid boiler is performed by this, simulated by this model and coupled with ANSYS fluid. And then the bed model and the entire simulation both validated in several perspectives. And then two numerical studies based on the simulation are conducted, which is for investigation of the waste of the physical change due to waste classification. Another one is MSW co-firing waste slush. Okay, let's go to the next section. The main work and the contribution from my project is the two models. The one is for the kinetic study. It is a universal description, and it's other than first order. It's for all the commonly used reaction mechanisms, and also the unique characteristics of the universal description has been conducted, which has been used to analyze the biomass pyrolysis process, and also conducting a simplified kinetic model with only one kinetics, and also it's getting validated. For the CFD simulation part, an in-house bed model is developed for the moving grid boiler, for the moving grid fuel bed, and including the NOx, and also the entire simulation is accomplished by the bed model coupling with ANSYS fluid simulation. And also two, numerical studies have been conducted aiming to investigating the feedstock change to waste classification and also for the co-firing of the sludge and with industry solid waste. That's I think that's important to the plant because maybe in the future they may use these two solutions to retreat or to adjust their boilers. Okay, even though I spent a lot of efforts on the two models on my projects, I have to admit there are some drawbacks on my works. First, for the kinetic modeling, the universal description should be extended to multi-step reaction mechanism. So far, it's only for the global reaction mechanism, and maybe even combining with some species evolution pathway models to extend the applicability. And moreover, the various or different biomass feedstocks need to be analyzed by the new kinetic model to get more reliable kinetics. For the combustion part, first, there are some improvements needed for the bed model. First, a complex submodel for describing the particle movements or motions need to be integrated into the bed model. And also the lateral heat transfer and all the thermal impacts of the grid needed to be considered when transforming the fixed bed model to the moving grid bed model. And also the bed model is deserved to be upgraded from thermally thin to thermally thick. But here maybe we need a reasonable compromise of the considering this and also the computational cost. And there is this more distribution kinetics or more reliable kinetics needs to be integrated in the bed model to achieve more realistic results. Actually, this is the initial idea of why I did such two work, and this is also on my to-do list. And at last, the NOx modeling actually is not being validated individually, and which I think may be better to validate the NOx with experimental data in the future to get more reliability of the overall model. Okay, let's go to the acknowledgements. First, I would like to acknowledge my supervisors, Professor Cheng Yi and Professor Torsten Burning, and also acknowledge my external supervisors, Senior Research Scientist Xuan Tianli, and Professor Ronnie Anderson, and Professor Wenchao Ma. And also, I would like to thank to my colleagues, co-authors, and reviewers. In the end, I would like to acknowledge the assessment committee, and thanks for taking your valuable time to assess my thesis, and also for coming today. Thank you.